In this video, we're going to talk about inflection points. You already know a fair bit about inflection points, you just don't realize it. So let's go back to chapter 6. Remember in chapter 6, you were asked questions about the concavity and convexity of a function. And to determine whether it was convex or concave, you use the second derivative. And we found that if the second derivative was greater than 0, it was convex. And if the second derivative was less than 0, it was concave. And you might have noticed that some functions were concave on an interval and convex on another interval. And so let's take a look at this function, this cube function that we have here. We've got y is equal to x cubed. Now let's figure out if this function is concave or convex. So looking at it, I can take the first derivative, and I see that the first derivative is 3x squared, so I'm using the power rule. And once I have the first derivative, I can find the second derivative. And the second derivative is equal to 6x. Now, let's do this a little bit formally. So we're going to do it formally in that I'm going to use a sign diagram. So I've got two factors. I've got 6, and I've got x. And if this thing is equal to 0, that's going to happen at x is equal to 0. And we've got the real number line in our top row. And maybe I'll move my 6 and my x down just a little bit. And 6, well, 6 is always positive, right? And x itself, well, if x is less than 0, then x is going to be negative. If x is greater than 0, it's going to be positive. Right? And so if I'm looking at the second derivative here, I see that if x is less than 0, all the way to negative infinity, I'm going to have a negative number. And if I have a negative number, for the second derivative, that means it's concave. Here, I'm going to have a positive number. So it's going to be convex. So what does this example have to do with anything? Well, what is an inflection point that we're going to be looking at? An inflection point, one definition anyway, is the point, the x value, at which a function turns from, or I won't say turns, I'll say changes from concave to convex, or from convex to concave. So x, if f of x is equal to x cubed, then x equals 0 is an inflection point. So you already knew how to identify whether a function was concave or convex, and it turns out right in the middle of these two things has a special name. That point has a special name. When a function starts turning from concave to convex, or when it turns from convex to concave, we call that an inflection point. Looking at the diagram, here's our cube function, and we already decided, or I sort of showed you, and explain to you that x equals 0 is an inflection point, and you can see that that's happening right here. So when x is less than 0, this function is concave, right? It's increasing at a decreasing rate. And when x is greater than 0, it's convex. And that point, when it changes from concave to convex, that's what we call an inflection point. Another way to think about the inflection point is the inflection point is the point at which the second derivative changes sign. And in order for it to change sign to go from, say, -1 to +1, assuming that we're dealing with the only continuous functions here, it's going to have to pass through a point where f double prime is equal to 0. Here's a sort of real-world example. You can imagine a ski hill. At the top, the function is concave up here. We're at the top of the hill. And if we're standing at the very top of the hill, if we step forward, we're going to be going downwards. And if we step backwards, we're going to be going downwards. The function is concave. At some point, maybe you could imagine that it's like, well, like here, extreme example, it's flat at the top. It's going to get more and more steep. The mountain's going to get more and more steep. And then at some point, in this case, the inflection point P, it's going to become more gradual. Maybe I can draw these just a little bit better. And so up here it's concave, and then down here it's convex. With the example we used before with the cube root, I showed you how to find an inflection point, but let's write out the algorithm explicitly. The first thing that you want to do when you're looking for inflection points is to find all points where the second derivative is equal to 0. The second derivative is equal to 0. Kind of like what we were doing in section 8.6. The next thing to do is to use a sign diagram to evaluate if the sign is changing whenever that second derivative is equal to 0. Because if the sign is not changing, then it can't be an inflection point. An inflection point is when the function changes from concave to convex or from convex to concave. And whenever that's the case, we're going to find that 2 is true. It's an inflection point. Let's do another example together. Let's find all local extrema and inflection points with this. So I'm going to start with the local extrema first, which means I want to take the first derivative of this thing, and I want to set it equal to 0. And that's going to give me 6x to the power of 5 minus 10 times 4 minus 40 x cubed. And now I want to follow the algorithm, and I want to simplify this as much as possible. So I'm going to factor out an x cubed. Let's see how that looks. Not bad. And now I'm going to factor out a 2. and that looks like I've gone as far as possible. As far as possible with simplifying this expression. Now I'm going to have to be a little bit careful here, but I'm going to write in the first column we've got 2x cubed, and we've got 3x squared minus 20. And I'm going to bring those down, give myself just a little more room. And I've got my real number line per usual. Now, remember this whole thing is equal to 0. So, well, pretty clearly, if x is equal to 0, this whole thing on the right-hand side is going to be equal to 0. What about in here? Well, if 3x squared is equal to 20, or maybe I'll write it as if 3x squared minus 20 is equal to 0, then we have x squared 20 over 3, and x is going to be equal to plus minus the square root of 20 over 3. And using my calculator, that's going to be approximately equal to 2.58. Oh, and I forgot to write plus or minus, right? Because it's squared. And so if x is plus 2.58, that factor is going to be 0. And if it's negative 2.58, then that factor is going to be 0 as well. So I'm going to have 2.58 over here and negative 2.58 over there. So I'll start with 2x cubed. If x is less than 0, then this thing is going to be negative. Now if x is less than negative 2.58, then x squared is going to become a larger number. And this expression, the second expression, this one right there, is going to be positive. If x is larger than negative 2.58, but less than 2.58 positive, then it's going to be a negative term. Of course, I forgot to finish off the top one. If x is greater than 0, the top one's going to be positive. And then again over here, when x is equal to 2.58, I plug that into here. I get 0. But if I get, say, 3, if I plug 3 into there, then I'm going to get a positive number. Now, what's happening with the first derivative? We're getting a negative value. So the slope, or the function f of x is decreasing. Then after, when x is larger than negative 2.58, we get a negative times a negative, which is equal to a positive. The function is increasing because the first derivative is greater than 0. Over here, we've got a negative, so it's decreasing again. And then over here, we've got a positive. And so what have we got? We've got a minimum. We've got a max. And we've got another minimum over there.